Hi everyone, today we're going to start talking about graphs of polynomial functions, but first please pause the video and give this quick warm-up a try. Alright, go ahead and check your answers. So remember, increasing means your slope is positive, so that would be here and here, but we describe the x values where that's happening, so negative infinity to negative 2. And then 1 to infinity, and I kind of estimated for those values. Decreasing means your slope is negative. That's happening from negative 2 to 1, so the x values where that's occurring. Positive, remember, means that your function is greater than 0 or above the x-axis. So that's happening here, which is from negative 3 to negative 1, and here, which is from 2 to infinity. And negative means your graph is below 0 or below the x-axis. So that's happening in these two intervals, negative infinity to negative 3 and negative 1 to 2. So before we start talking about graphs of polynomials, there's some important vocabulary we need to know. First, just generally, what is a polynomial? It's a number variable or the product of a number and one or more variables with whole number exponents. That's the key to these. Whole number exponents, meaning positive integers. So you'll see down here we have some examples of polynomials, right? It can have as many terms as you like. The terms can have any whole number exponent. Some of the terms will be constants, meaning there's no variable, but if you look at the non-polynomials here, you'll see a negative exponent. That is not a polynomial. Here you see a square root. That's not a polynomial. Here you see a rational term. That's not a polynomial. So it's only when you have terms with whole number exponents or constants. So polynomial functions are simply functions that are defined by a polynomial expression. So they follow those same rules. Standard form is something we'll be working with a lot today. That's when you take your polynomial and you list it in what's called descending order, which means you're going from the highest degree variable to the lowest degree variable, and then you end with the constant. So you're listing your terms in that order. So here we have some common polynomials that actually have set names. So if you just have y equals a constant, like y equals 5, we call that a constant function. We're going to talk about the degree in a second, but just for a sneak peek, it is the largest exponent that you see. So here we don't see an exponent, our degree is 0. If you just have y equals 2x plus 5, your degree is 1, that's your highest exponent. That's just a linear function. When your degree is 2, so your highest exponent is a 2, we call that a quadratic function, as we learned about last unit. If your highest exponent is 3, we call that a cubic function, 4 a quartic function. Beyond that, I mean, we can just classify them as a polynomial, and all of these can also be classified as polynomials. They just have more specific names. Okay, so we're going to start with something simple. We're going to rewrite the polynomial in standard form and then evaluate the function when x is 3. So first I'm going to look for the term with the highest degree, or the highest exponent, which is that 2x to the 4th. It is positive, so we keep it positive. The next highest degree, maybe I'll cross them off as we go, is the squared term. So this squared term is negative, so we have to keep that negative. It's negative 8x squared. The next highest is just my x term, so I say plus 5x, and then my last term is my constant, which is minus 7. So this is in standard form, and now I'm going to evaluate the constant at 3. So I'm doing f of 3, so 2 times 3 to the 4th minus 8 times 3 squared plus 5 times 3 minus 7. I want to remind you that we always follow order of operations, so we always do exponents before we multiply. So 3 to the 4th is 81, so it'll be 2 times 81 minus 8 times 3 squared is 9, and then here we can just do these terms, and then let's do our multiplication. So here we have 162 minus 72 plus 15 minus 7, so that gives us f of 3 equals 98. There you have it. All right, go ahead and pause the video and give this one a try. All right, go ahead and check your work here. Here's the polynomial written in standard form. And then if you plug in 4, you should get negative 129. Okay, so now we're going to start talking about the graphs of polynomial functions. We won't be doing any graphing today, but we're going to start learning about some key features. So to graph a polynomial, we look for 4 important parts that we'll use to guide us when we actually go to graph. So the first thing we're going to look for is what's called the leading coefficient, which is the coefficient of the term with the highest degree. If your equation is written in standard form, it should be the coefficient right out front, which is why we like to start by writing in standard form. Then we look for the degree of our function. The degree of the entire function is the highest exponent of any individual term, which again, if it's written in standard form, should be that first term. So the highest individual exponent is the degree of your entire function. We will also look for zeros, which are x-intercepts. We're not going to be looking for that today, but that's going to be another key feature. And we'll also look for the y-intercept, which will always be the constant, and you can always find it by setting x equal to 0. So let's start with that leading coefficient. What does the leading coefficient tell us? So the leading coefficient of any polynomial function tells us the end behavior as x approaches positive infinity, which means on the right. So it only tells you the end behavior on the right side of the graph. If you want to figure out what's happening on the left side of your graph, you're going to need to look at the degree. The degree of our function tells us if our end behavior matches or is opposite. And we'll elaborate on that in just a second. But again, the leading coefficient only tells us the end behavior on the right, and then the degree tells us if the left side matches or if the left side is opposite. So let's start with cases where our leading coefficient is positive, which you see here and here. If your leading coefficient is positive, the right side of your graph approaches positive infinity, or you can think of it as the right side goes up. That's what the leading coefficient tells us. If the leading coefficient is positive, the right side goes up. If the leading coefficient is negative, the right side goes down. So remember, the leading coefficient only tells us what's happening on the right side. Positive means it goes up, negative means it goes down. So I like to start by drawing a little arrow either facing up or down. Then you look at the degree. If your degree is odd, your end behavior is opposite. So odd, I like to say they both start with O. Odd means opposite. So you could see that here and here. So odd means opposite. So if you already know this side goes up, then the other side would go down. Or if this side goes down, then the other side goes up. Odd means opposite. Now, even means that your end behavior matches or is the same. So here, if the right side goes up, so does the left side. If the right side goes down, as you see here, so does the left side. So even degree matches, odd degree is opposite. So I always start with the leading coefficient and I mark my arrow, and then I look at the degree to tell me how my arrow should point on the other side. So that's what we're going to be focusing on today, just the end behavior of our polynomial. All right, let's give this one a try together. First, we're going to rewrite the function in standard form. Then we're going to list the leading coefficient and degree, and then we're going to use those to determine our end behavior. So first, p of x equals, I can see the largest term is 6x to the 4th, and then negative 4x cubed, and then 1/2 x squared. I do want to point out, again, it's totally fine to have a coefficient that's a fraction. It's just your exponents cannot be fractions. And then plus 3x, then minus 1. So that's our standard form. And then our leading coefficient, we can see, is the coefficient of the term with the biggest exponent. Our leading coefficient is 6, which is positive. That's really all we care about, is the sign of our leading coefficient. And then our degree is 4. It's our largest exponent of any individual term. And I'm going to make a note that that means it's even. So since our leading coefficient is positive, that means that the right side of our graph goes up. So that tells us as x approaches positive infinity, this just means to the right, f of x approaches positive infinity. The leading coefficient tells us the end behavior on the right. Now, since our degree is even means our end behavior matches. So this side will also go up. Even means match your end behavior. So that means as x approaches negative infinity, which means going to the left, f of x also approaches positive infinity. And that's it. All right, let's try another one together. So let's start by rewriting this function in standard form. So negative 2x to the 5th. Don't lose your negative, it sticks with the term. Plus 5x squared plus x plus 3. So I can see that my leading coefficient is negative 2, which again we care more about the sign than the actual value. Our degree of the entire function is 5, which we really care right now if it's even or odd. And now we can move on to end behavior. So since our leading coefficient is negative, that tells us that the right side goes down. It only tells us the end behavior on the right. So as x approaches positive infinity, f of x approaches negative infinity. This says on the right my graph goes down. That's because the leading coefficient is is negative. Now I look at the degree and I see that it's odd. Odd means opposite. So since this side is going down, I know that this side must go up. So I know that as x approaches negative infinity, f of x approaches positive infinity. And that's it. All right, at this point, go ahead and pause the video and give this one a try on your own. All right, go ahead and check your work. Here you can see our leading coefficient is negative 6. So since it's negative, that tells us on the right my graph goes down, which is this line of the end behavior. On the right my graph goes down. Then we see that our degree is 4, which is even, which means our end behavior matches. So this side goes down because the right side goes down and my degree is even. So that is described on that second line of end behavior. All right, so now we're going to kind of do the opposite. We're going to look at some graphs and describe what we know about the leading coefficient and the degree. So for the leading coefficient, I'm going to abbreviate it with LC. I just look at the right side of my graph. I'm noticing that the right side is going up, so that all I can tell is that my leading coefficient is positive. That's what I know. The next thing I look for is if the left side matches or is opposite. I see that the left side matches, so that tells me that the degree is even. Okay, let's look at this second one. I look at the right side of my graph. The right side is going down. That tells me that my leading coefficient is negative. And then I see if my end behavior matches or not. I notice that my end behavior is opposite. One side goes down, one side goes up. That tells me that my degree is odd. And there you go. All right, go ahead and pause the video and give this last one a try on your own. All right, here the right side is going up, telling us our leading coefficient is positive, and I can see that my end behaviors are opposite, telling us that our degree is odd. All right, that is all for today's video. Thank you so much for watching.